Yeah, Martha, can you able to hear my voice now? You can, yeah, you can type Avanti live too. Okay, so there you will get it. Or else I will tell you at the end of the class. Okay. Hey, good afternoon, students. Let's wait for others to join. Okay, so just stay in the call for a while. Yeah. Good afternoon, students. Good afternoon to all of you. I hope I am visible and audible to all of you. Just let me know in the chat box if I am visible and audible. Yes. What about others? Can you all able to see me, hear me, and able to hear my voice? And can you able to see my screen? Yes. Okay. Okay. Great. So let's start with the today's session. Let us recall the thing which we have discussed yesterday first, and then we will move on to the new thing. Okay. So here is a recall test questions for you. So here the two questions for today's session is, first thing, you need to find out the formula to calculate the molar mass from relative lowering of vapor pressure. So relative lowering of vapor pressure is one of the colligative property, right? So yesterday we have discussed that, and I have given one formula at the end. Okay. So if you can able to actually the typing the formula in the chat box is little bit difficult only. So I will give you the answer for that here. And you can go for the second question. You can think of one example which I gave for minimum boiling azeotrope. Okay, so these two are the questions. I'll give you the formula for the first question. So the formula to find out the molar mass from relative lowering of vapor pressure colligative property is P1 naught minus P1 divided by P1 naught, which is equal to W2 into M1 divided by M2 into W1. Okay, so this is the formula. So just try to recall this. I hope you all have memorized this formula. Am I right? Have you all memorized? Have you all memorized the formula? Yes? Did you guys memorize the molar mass formula of RLBP? This formula, yes or no? Yes. Very good. Fine. Now, coming to the second question, give an example for minimum boiling azeotrope. So, what is an example which we have studied yesterday for minimum boiling azeotrope? Ethanol and water. Very good. Very good. So, Janvi, Kadapaswan, can you able to mention the percentage of ethanol and percentage of water which we have discussed yesterday? What is the percentage of ethanol and percentage of water? Very good. Very good. Yes. Yes. So it is 95 percentage of ethanol and 5 percentage of water. Okay. So this is an example for minimum boiling azeotrope which shows positive deviation. Okay. So now moving forward to the today's learning objectives. So we are dealing with colligative properties, and yesterday we have seen the types of colligative properties. Just I gave you the headings, and we have discussed one among those types, right? The first is relative lowering of vapor pressure. Second is elevation of boiling point. Third is depression of freezing point. And the fourth one is osmotic pressure. Okay. Now, yesterday we have discussed everything in detail about the relative lowering of vapor pressure. Okay. So I told you, we have to take a volatile solvent first. Then we have to add a non-volatile solute to that. And by doing so, the vapors which is coming out from the solution will get decreased, and that we call it as relative lowering of vapor pressure. And from that concept, we have discussed, we have seen one formula which I have shown you in the previous slide. Okay. Now, moving on to the second colligative property, which is the elevation of boiling point. So, before moving on to the elevation of boiling point, I would like to give you some information about boiling point first. Okay. So, can anyone give me the definition for boiling point? Then later on we will discuss it. What is boiling point? If somebody or if I ask you what is boiling, what will be your answer? So try the answer for this question. What is a boiling point? Nobody is getting the definition of boiling point. Students, what is boiling point? So we have come across this term for long, right? Okay, the point where the pressure of the component is equal to the atmospheric pressure. You are exactly correct. Very good. Yamarthi and Sneha, both of your answers are exactly correct. Very good. Let's discuss that. Okay. So here I have a container, okay, in which I have some substance. It's so ice cubes. Yes, yes, yes. Very good, Veera Prasad. Great. So now this water has some internal pressure, or we call that as vapor pressure. Okay. And we also have some pressure outside this. So that we call as external pressure or the atmospheric pressure. Okay. When the external pressure becomes equal to the internal pressure, when the external pressure is equal to the internal pressure, what happens? The substance will boil. Okay. So boiling happens in that. And the temperature at which the boiling occurs for that particular component is called as boiling point. Okay. So the substance will have the component will have some pressure that we call as internal pressure, and also the atmospheric pressure is there, which is external pressure. When these two pressure become equal to each other, then we call that point as the boiling point. Okay, clear for all of you? So now let's see a graph. So with the vapor pressure and temperature. Okay, so let me show you. So here the atmospheric pressure is 760 mm of mercury. Okay. And here I have 273 Kelvin, and here I have 373 Kelvin. Okay. And this 373 Kelvin is the normal boiling point of water. Right. So this is a curve of water. Boiling point of water is 100 degrees Celsius. And in terms of Kelvin, I have to add that 100 to 273, right? So it becomes 373. So at this particular point, the water will boil, and we call that point as the boiling point. Normal boiling point. Atmospheric pressure will be 760 mm of mercury for water at that point. Got it? Now, what is going to happen if I add some non-volatile solute to that pure water? That is what we are going to see here in the next slide. Got it? So again, I am going to take the same graph with the vapor pressure and temperature. Initially, I will have only the pure solvent. Initially, I will have only the pure solvent. Yes, Nagashri, your answer is correct. So initially, I have only the pure solvent, which is A here, and that is the water we can take. So I have only the pure solvent, and that this pure solvent is volatile in nature. It is volatile in nature, and that particular solvent will boil at one particular temperature. So I call that as TB naught. So this TB naught denotes the boiling temperature of the pure solvent. So this point denotes the boiling point of the pure solvent. Okay. TB naught is the boiling point of pure solvent. Now what I am going to do? I am going to add a solute. Okay. I am going to add a solute B. And what is the nature of the solute? It is non-volatile. Right. So the nature of the solute is non-volatile. So what will happen if I add a non-volatile solute to this solvent? It will form a solution. The solute and solvent particles will form a solution. So this is the boiling point of solvent. Now after adding the solute, I will get a solution. Now what is happening here? The temperature, the boiling temperature of the solution is increasing. Okay. Suppose if this is around 300 Kelvin, then this is 400 Kelvin. Okay. So this is the solvent line and this is the solution line. So the boiling temperature, the boiling point of the solution is more compared to the boiling point of the solvent. Okay. And the difference between these two will give the delta TB value, which is called as the elevation. Elevation means rising. Okay. Elevation means rising. So delta TB is the difference between these two, boiling point of the solvent and boiling point of the solution. So usually delta TB can be written as final minus initial, right? The final is 400 Kelvin, which corresponds to TB, and the initial is 300 Kelvin, which is TB naught. So using this formula, we can calculate the delta TB. Got it? Got it? Is it clear to all of you? So if I am adding a non-volatile solute to a volatile solvent, the boiling point of the solution increases. Got it? This is the concept. So do any of you have any doubt from the concept and the graph which we have discussed here now? Are you all clear with the terms? TB naught, TB, and what is delta TB and all? Should be very, very clear, okay? Do not have any confusion. So if I'm putting naught, if I'm putting 0 in the superscript, then it denotes the pure component, which is a solvent. Got it? And TB is the vapor pressure, boiling point of the solution, and delta TB is the elevation of boiling point. Now we will see some formulas for this elevation of boiling point, like we have seen for the relative lowering of vapor pressure. Okay. Now, from the experiment for dilute solution, what happens? Delta TB will be directly proportional to molality. So this small m denotes the molality. And if I remove this proportionality symbol, I have to introduce a constant, right? So that constant is called as Kb. So delta Tb is equal to Kb into m. So what is the name of this Kb? So this Kb has three names. Okay. So the first name is molar elevation constant. Second name is boiling point elevation constant. Third name is ebullioscopic constant. So how many names does this Kb has? Three names. Molar elevation constant, boiling point elevation constant, or ebullioscopic constant. And now what we have to do? We have to substitute the thing for molality. So can anyone give me the formula for molality? So in the beginning of this lesson, we have discussed the formula for molality. What is the formula? It was the name given by the scientist, ebullioscopic. Yeah. Is it moles by volume? Molality.
Number of moles of solute by mass of solvent in kgs.
Very good. I don't know who is speaking. May I know your name, please, my dear?
JNV Kammam.
Jamie?
JNV Kammam, Sirisha.
Okay, okay. Okay, okay. Good, great. So, can you repeat the answer once again?
Number of moles of solute by mass of solvent in kgs.
Yeah, Risha, right? Yeah, very good. Number of moles of solute by mass of solvent in kilogram. Very good. Yes, many of you are giving me the correct answer. Good. Now, if I substitute that here, what I will get? It will be W2 by M2 into 1000 divided by W1 in terms of gram, right? Number of moles of solute by mass of solvent in kilogram. So number of moles is equal to mass by molar mass. This is mass of solvent. Number of moles is equal to mass by molar mass. So mass of the solute is W2. Molar mass of the solute is M2. And in the denominator, I have the mass of the solvent also. So mass of the solvent is W1. Now if I convert this to this kilogram to gram, then I have to divide it by 1000 and that will go to the numerator. Okay, so from this only I have got this relation. Now I have to take this m value and substitute here in this formula. And if I substitute, I will get delta Tv is equal to Kb into 1000 into W2 by M2 into W1. Okay. So this is the very important formula you have to study from the elevation of boiling point topic. Okay. So this is the formula which is being used to calculate the molar mass of the component using this elevation of boiling point. And also the formula which I have already given for delta Tb. So delta Tb is equal to Tb minus Tb. This is also again very important. Clear? Any doubt from this? So we also have unit for Kb. This Kb has, this ebullioscopic constant has some units. It is Kelvin kilogram per mole. Okay. And this Kb has one more relation, R into M1 into Tb square divided by 1000 into delta H of vaporization. Okay. What is delta H of vaporization? Enthalpy of vaporization of the solvent, and the Kb for water at 373 Kelvin. 373 means at 100 degrees Celsius. The Kb value for water is 0.52 Kelvin kilogram per mole. Okay. So you have to memorize this value also, because in some questions they will give you this value, in some questions they will not give. So in that case, you should know that Kb for water at 100 degrees Celsius is 0.52 Kelvin kilogram per mole. Okay. So from this slide, what you are getting, you are going to learn these two formulas. Okay. And you are going to learn the three names of Kb and the unit, the relationship between Kb and delta H of vaporization. And at last, the Kb value for water. Okay. So shall we solve one question from elevation of boiling point using these formulas? Do any of you have any doubt from the elevation of boiling point topic? Shall I go for the next slide? Okay. What about others? Only Harish is saying no. What about others? Shall we go for the question? Okay. If you want to take down anything from this slide, you can let me know that also. Okay. So I will wait for you so that you can take. Okay, many of you are going for yes, so I will go for the next question. This is the question. A solution containing 12.5 gram of a non-electrolyte substance in 175 gram of water gave boiling point elevation of 0.70 Kelvin. Calculate the molar mass of the substance. And Kb for water is given here. So how to solve this? We have to find out the molar mass of the substance. So we have two components. One is the solvent, which is A, and the other one is the solute, which is B. Okay. So what are the given information? A solution containing 12.5 gram of a non-electrolyte substance. So the non-electrolyte substance is a solute and its mass is given. So W2, A or B, or you can keep this as 1 or 2 also. Okay, W2 is 12.5 gram. In 175 gram of water, water is a solvent and its mass is also given 175 gram. Gave boiling point elevation. Boiling point elevation, there is an increase. Okay, in the boiling point value. So that is the delta TB value. This is the boiling point elevation of 0.70 Kelvin. Calculate the molar mass of the substance. So M2 we have to find out. And M1 for water, it is easy, right? Yesterday we have calculated. So for H2O, the molar masses, for one hydrogen it is 1, for two hydrogen it is 2, for one oxygen it is 16, so it will be 18. So the molar mass of water is 18. Okay, clear? And also we have Kb. So we have Kb in the question. So which formula we have to use? Delta TB is equal to Kb into 1000 into W2 by M1, M2 into W1. Delta TB value is given, Kb value is given, W2 is given, M2 is asked, and W1 is 175 gram, and substitute all the values here in the question, here in the formula, and get the value of M2 by rearrangement as 53.06. Okay. So can you all able to understand how to approach? You have to practice to take out the given information from the question. That's all. Okay. So otherwise, everything is easy only. You just have to take the formula and substitute those things. That's all. Rest all with multiplication and division only. So you have to memorize this formula and then you should know to take out the given information from the question. So these are the two things you need to do. Okay, for that you need practice. If you are solving one question per day, you'll get used to it, how to approach this kind of question and solve it. All right. Any doubt? Shall we go for the third property? What about others? Okay, okay, okay. I'm waiting. I'm waiting. Srikanya, I'm waiting for you. Let me know once you are done with it. So, what is the first colligative property? Relative lowering of vapor pressure. And there we have solved one, we have studied one formula, and in elevation of boiling point, we have studied two formula. One is to find out the molar mass and the other one is to find out the delta TV. Here in this question, delta TV is given. So that's why we did not use that delta TB is equal to TB minus TB not formula. Okay. In some questions, they will not give you, you have to calculate that using the information and then you have to substitute. Yes. So you are done with it now? Okay, fine. Now we'll go for the third property. So the third property is depression of freezing point. So like boiling point, can anyone give me the definition for freezing point? What is the definition for freezing point? What is the definition for freezing point, students? Why all of you are staying so silent? You know or you don't know? Okay, let me give you the definition. So it is also the temperature at which the vapor pressure of liquid becomes equal to the vapor pressure of the frozen liquid. Okay, freezing point is the temperature at which the vapor pressure of the liquid becomes equal to the vapor pressure of the frozen liquid. Okay, so this is called as freezing point. Now, what is going to happen to this freezing point on addition of the non-volatile solute to the volatile solvent? So that we will discuss. So the same graph I am going to take. Okay. So initially we have only the solvent. The same story. Okay. Initially we have only the pure solvent component, which is the first component or component A. And the nature of the solvent is volatile. Nature of the solvent is volatile. And this particular solvent might have had some freezing point value and uh, it has some temperature. Okay. For water, the freezing point is actually 0 degree. Okay. So let it be as 0 degree. Now what I'm going to do, I'm going to add a solute, which is component 2. And the nature of the solute is non-volatile. So if I add the solute to this solvent, so it will form a solution again. So what is the freezing point of that solution? Whether it will increase or it will decrease. So this is the frozen solvent. This is actually the liquid solvent curve. Okay, this is the liquid solvent curve in which I have only the pure solvent. Yeah, very good, Sneha. So that particular solvent has some temperature, which is the freezing temperature of the solvent, and it is denoted as PF naught. Okay, freezing point of the pure solvent. Now, after adding the non-volatile solute, the solvent, liquid solvent will little bit get frozen. Okay, so we will have a frozen solvent and for the solution. Okay, and this line corresponds to PF, which is called as the freezing point of the solution. And if I take the difference between these two, It is denoted as delta TF, which is actually the depression of freezing point. Now TF is having the lowest value compared to TF naught. So how to calculate delta TF? So delta TF is equal to final minus initial. Now the final is TF naught and the initial is TF. So for delta TB, what was the relation? It was TB minus TB naught because the boiling point got raised there. So this is the final. This is for solution. Now here what has happened? The freezing temperature of the or the freezing point of the solution is getting depressed. It is getting lowered. So it is having the very least value. So the final is greater than the initial. Okay, TF naught minus TF. Got it? So don't get confused between these two. Should be very clear. Now we'll see some formulas like we have seen for boiling point. Again here the delta TF is directly proportional to molality. Now if I remove this proportionality symbol, I have to introduce a constant which is called as Kf. Okay. So here Kf is also has three names. The first name is molar depression constant. Second is freezing point depression constant. And the third name is cryoscopic constant. Okay, their molar elevation, here molar depression. Their boiling point elevation, here freezing point depression. Their ebullioscopic constant and here cryoscopic constant. That's all. Okay. So if you relate these two and study, it will be easy. Now you have to put the formula of molality here. Okay, the same formula. And if we substitute that molality formula, we'll get this equation. So what is the difference between these two formula? Instead of delta TB, we have delta TF. And instead of KB, we have KF. The remaining things are same. Okay. And this is a formula for delta TF. Okay. The remaining things are going to be same. You have to memorize these two formulas properly. Okay. And what is the unit of KF? It is Kelvin kilogram per mole. And also we have one relationship between Kf and delta H of fusion. So there it was delta H of vaporization because that is the boiling point. So when a liquid boils, it produces the vapors, right? But here it is about the freezing point. So what happens? So the molecules will come closer to each other. They will get fused with each other. So the enthalpy of fusion of the solvent is related with Kf. Okay. And like Kb, we have Kf value for water at 273 Kelvin as 1.86 Kelvin kilogram per mole. Okay. So again, I'm saying you have to memorize the value of Kf for water at 273 Kelvin. 273 means it is 0 degrees Celsius. Okay. 0 degrees Celsius. So Kf for water at 0 degrees Celsius is 1.86 Kelvin kilogram per mole. So this is clear. Any doubt from this? Same thing you have to take it down. So the two formulas, the three names of Kf, and the relationship between Kf and delta H of fusion, and at last the Kf value for water. Okay. Clear for all? Clear for all? Why only for dilute solution? Because we cannot go for the concentrated solution, right? Because here we have a pure solvent. Solvent is the major part. Like we'll have 80% of solvent, okay? And only 20% or 10% of the solute, non-volatile solute present inside the container. So the major portion is of solvent, means it is the dilute solution, right? If it is a concentrated solution, the solute will be more compared to the solvent. But the thing which we are taking is the solvent will be more. Clear? So only for dilute solutions, we can able to apply those things. Okay. If the solution is concentrated, you cannot do many experiments, because if something is very concentrated, we cannot touch it or we cannot do the experiment properly, only for dilute. So whenever we are doing some experiment, the thing is we'll dilute that solution, we'll do it. So that's why from experiment we are getting these values. Got it? Okay, fine. Now, coming to the last colligative property, can anyone give me the name of the last colligative property? Can anyone give me the name of last colligative property?
Osmotic pressure.
Very good. It is osmotic pressure. Relative lowering of vapor pressure, elevation of boiling point, depression of freezing point. Now, we have come to the last property, which is osmotic pressure. Before moving on to osmotic pressure, so let's see something about osmosis and then we will go for the osmotic pressure, okay? All of you can able to see the picture on the screen, right? What it is? What is given in this picture? Raw mango. Very good. So mango. So I hope many of you like mango. Am I right? Yeah, I like mango very much, Okay, fine. Now let's. Rikanya also likes mango very much, it seems. Fine. Now, now you see this. So this mango is now dipped in the brine solution. So what is meant by brine solution? It is a salt solution. Okay, if I keep this mango inside the salt solution for some time, the fresh raw mango is turning like this. Okay, looking like a old mango, no? Somewhat. Doesn't look good, no? But anyway, it tastes good, but it doesn't look good. That's it. Then coming to the next picture. What is this? So I have some roses. Yeah, it is a rose. This is the fresh rose. Yeah, after adding fresh water, I get a rose like this. Yeah, dried rose petals. Dried rose and fresh rose. Very good. So, what do you understand from this? So, what is happening? If I put the mango in the salt solution, it is getting shrinked. Okay. If I put this rose, the dried rose into the water, it is becoming fresh. So what is happening here actually? Yeah, this is due to, okay, something is going from higher concentration to lower concentration. Okay, fine. So these are the day-to-day practical phenomena in which the osmosis occurs. Okay. Now let's see the definition of osmosis. Yeah, very good, very good. So osmosis is the process of flow of solvent molecule through the membrane from pure solvent to the solution. Okay, process of flow of solvent through the membrane from the pure solvent to the solution. So, in the GIF which you can see here, so this shows the process of osmosis. So, in one side, I have the pure solvent, okay? And membrane is separating the solvent, and in the other side, I have some salt molecules. Okay, this is a salt molecule. What is happening here? What is happening here? Yeah, it is a semi-permeable membrane. Membrane is a semi-permeable membrane in which I have some small holes. Okay, I have some small holes. So what is happening here? Solvent, the pure solvent molecules are passing through the semi-permeable membrane to the solution side. Okay, to the salt solution side. In this case, it is passing through the salt, solution, side. Okay, once again you can watch this. So I have a solvent and I have a solution. So the solvent molecules, they are passing through the semi-permeable membrane to the solution side, Okay, and we call this process of flow of solvent through the semi-permeable membrane from solvent to solution as osmosis. Okay, so this is osmosis. So all of you can able to understand from the picture, right? Now we'll go for osmotic pressure. So let me give you the osmotic pressure definition. So it is the excess pressure that must be applied to prevent the osmosis. The excess pressure that must be applied to prevent this osmosis. And osmosis is not the colligative property. Osmotic pressure is the colligative property. Got it? Osmotic pressure is the colligative property. It is the excess pressure which has been applied to prevent this osmosis process. Okay. And this osmotic pressure is denoted by the letter pi. Okay. And this osmotic pressure depends on the concentration of the solution. So, osmotic pressure is dependent on the concentration of the solution. So, I have one relation which relates these two, which is pi is equal to CRT, where C is the concentration, and we have seen 7 concentration term now, and here the concentration is molarity. The term which we are using here is molarity. So, concentration is equal to number of moles of the solute divided by volume of the solution in liter. So, that is the formula to find out the molarity. So, in place of C, you can substitute N2 by V. So, why I have put N2 here? Can anyone tell me why I have substituted 2 here?
Solvent.
Sorry? Why it is written as N2?
Number of moles of solute.
Very good, very good. It is the number of moles of solute. Solute is usually represented as 2, no? For solvent we use 1 and for solute we use 2. So the number of moles of solute divided by volume of solution in liter, and that is molarity. So that's why we are putting N2. So in place of C, substitute N2 by V, where R is the gas constant and T is the temperature in Kelvin. Okay. And also we know that number of moles is equal to the given mass by molar mass. So do you all know this formula? Number of moles is equal to given mass by molar mass. You might have studied this formula from your class 11 onwards. Okay, number of moles is equal to given mass divided by molar mass. So the given mass of solute divided by molar mass of the solute. So in place of N2, we can substitute W2 by M2. On substituting, I will get equation like this, and in this, from this equation, I have taken this B to the other side. So that's why I have got pi B here in the left hand side, which is equal to W to RT by M2, and taking M2 to one side and bringing all others to the other side, we are getting W to RT by pi B, where M2 is the molar mass of the solute. So using osmotic pressure, we can able to find out the molar mass of the solute particle using this formula. So this is very important. So all the formulas are important. All the 3 formulas are important. All the 3 means I will tell you who are those 3. Okay. So this is formula number 1. And this is formula number 2. This is formula number 3. Okay. So these 3 formulas are important. According to the question, you have to substitute. If concentration is given to you directly in the question, then you can go for this first formula. Okay. If number of moles is given to you, if number of moles and volume both are given, then you have to use the second formula. If only the mass is given to you, then you have to go for the third formula. Got it? So you have to look into the question. So according to the information given in the question, we have to take the corresponding formula and solve accordingly. Clear? It is easy only. Very easy. Just memorize. Even if you forget, no issues. You can take all the three formulas from the first formula. If you know these relations. Okay, if you know these two relations, you can get all the formulas from the first. So students, any doubt till now? All of you can able to understand what is osmosis and osmotic pressure, right? Shall I go for the uses of osmotic pressure and uses of osmosis? Yes. So this osmotic pressure method is used to determine the molar mass of the protein, polymers and other macromolecules. So mainly osmotic pressure is the only colligative property which is used to calculate the molar mass of the macromolecule. Protein, polymer, everything will come under this macromolecule. Carbohydrates, proteins, fats, vitamins, minerals, all those things are macromolecules, right? So the only colligative property which is used to find out the molar mass of macromolecule is osmotic pressure. This is one of the very important question. This is one of the very important question you will get. So this was one of the previous year question also. Long back they have asked this question in NEET exam, I think so. Okay, so you should remember this. Among the four given property which is used to find out the molar mass of macromolecule, the answer is osmotic pressure. Okay, so here I am closing the osmotic pressure topic. Okay, and some little more informations are related to this osmotic pressure. So we will do that also, and we will wrap it up this osmotic pressure totally within few minutes. Okay. So here in the next slide, I'm going to talk about isotonic solution. So what does mean by iso? Can anyone give me the definition for iso? Not the definition, meaning. What is the meaning of iso? Yeah, same. Isotonic solution means something is going to be same. So what is that something? That something is osmotic pressure. Okay. Solutions having same osmotic pressure is called as isotonic solution. So I'm going to have two solutions. One is solution 1 and the other one is solution 2. So both will have osmotic pressure. One is having pi 1 and the other one osmotic pressure is pi 2. If the pi 1 is equal to pi 2, then we call those solutions as isotonic solution. Okay. We know that pi is equal to CRT, pi 1 is equal to C1RT, and pi 2 is equal to C2RT. Right? So I can equate. If left hand sides are equal, then I can equate the right hand side. So RT is same, so I can cancel out. So C1 is equal to C2. So concentration of solution 1 is equal to the concentration of solution 2. Means there is no osmosis occurring between them. Okay. For example, I am taking 0.9 percentage of NaCl solution, which is isotonic with blood plasma. Okay. So if blood plasma is inside this 0.9 percentage NaCl solution, there is no osmosis occurring between them. Okay. I'll give you the pictorial representation so that you can understand it better. So I'm going to take a blood cell. Okay, I'm going to take a blood cell and I'm going to place it in a sodium chloride solution. Okay. So see here. If the NaCl solution concentration is more than 0.9 percentage, the water molecules which are present inside the blood cell, they are coming out. Harish, you want the previous slide? Okay. Finish it fast, finish it fast. Let me know if you are done with it. Harish, have you completed? Okay. So Now guys, listen. So what is happening here in the first case? So water molecules which are present inside the blood cell is coming out. Okay, if this is the case, then it is hypertonic. Then the solution is called as hypertonic solution. Okay, and if the solution is equal, concentration is equal to 0.9 percentage, the flow of water molecule into the cell and the water molecule coming out of the cell will be equal. Means it is isotonic solution. Okay, and in the third case, if the solution is concentration is less than 0.9 percentage, then what happens? The water molecules which are present outside this blood cell will go and enter into the blood cell and the blood cells will get bulged out. Okay, then it is called as hypotonic. It is called as hypotonic. Okay, if the flow of solvent is equal, it is isotonic. If it is going out, if the water is coming out, the cells will shrink, then that is hypertonic. If the water molecule is coming inside the cell, it is getting bulged out, then it is called as hypotonic. Clear for all of you? So this is all about the osmotic pressure. Okay. Now the next is reverse osmosis. What is reverse osmosis? Opposite of osmosis. If the pressure of the solution side is greater than the osmotic pressure, then we call it as reverse osmosis. Okay, you see here, I am applying some pressure on the solution side and that pressure is greater. So what is happening? The molecules which are there on the solution side is moving to the solvent side through the semi-permeable membrane. Okay, so in the osmosis case, solvent molecules traveled through the membrane to solution side, but in reverse osmosis, the molecules from solution side is moving to the solvent. So why it is happening? Because the pressure which I am applying on the solution side is greater than the osmotic pressure. Okay. Example are the uses of this reverse osmosis, desalination of seawater. So most of you might have had this reverse osmosis RO in your home, right? The filter water which we are using in our home. It is following this process only. Okay. So to take out all the ions which are not good for health or to filter it out, we use reverse osmosis process. And all of us, many of us will have this RO in our home. I think so. Okay. So it gives us only the water which contains very small ions which are good for health. Okay. So this is about reverse osmosis. Now, lastly, we have one small topic which is called as Van 't Hoff factor. So Van 't Hoff is the name of the scientist and it is denoted by the letter I. So in some cases means in some association or dissociation of molecule, what happens? We cannot find out the correct molar mass values from the colligative property. Okay, due to some association or dissociation. So in that cases, what happens? There will be some abnormality from the normal molar mass value. Okay, so that abnormality can be found out using the Van 't Hoff factor I. So that can be rectified. That abnormality can be rectified using this I. Okay, so we have one formula for calculating I. It is equal to normal molar mass by abnormal molar mass. We also have one more formula, observed colligative property divided by calculated colligative property. And also we have one more formula, total number of moles of particle after dissociation or association by number of mole of particle before association or dissociation. Okay. So all these three denotes the same thing only. You don't have to worry. Okay. To find out the value of I, they will give you the normal molar mass, abnormal molar mass, everything in the question. You just have to substitute and divide it and get the value of I. Okay. For dissociation, I value will be greater than 1 and for association, it will be less than 1. So you have to Keep these two things in your mind. Okay? And you have to memorize these formulas. That's all. Values will be given. You just need to substitute. That's all. Clear for all of you? And then moving forward with this Van 't Hoff factor, we have got the modified equations for colligative property. So what I'm going to do here, I'm going to take all the four formulas which we have studied for colligative property. Okay, Harish, you want me to show the previous slide? We are running out of time and we are about to complete and going very fast. Sorry for that, my dear students. This I will complete it within 2 minutes or 3 minutes. Okay. So try to concentrate more. Harish, shall I go for the next? Yeah. So now the abnormality has got rectified with the term Van 't Hoff factor I. Okay. And we are getting the modified equations for colligative property in which this factor I is going to get multiplied with all the four properties. Okay. First, let me take relative lowering of vapor pressure. And this was the formula we have seen, and it was multiplied, it is being multiplied with I. Then for elevation of boiling point, we have studied delta TB is equal to KB into M, I is multiplied. For depression of freezing point also the same case. And for osmotic pressure also, it is multiplied with CRT. So very easy. Find out the value of I, multiply with the colligative property formula. That's all. So is it clear? Any doubt? I will give you one question. You can take this as a homework and solve it by yourself. Okay? All of you guys can take the screenshot of it and you can do it on your own. Okay? Check whether you are getting the pi value as 5.21 or not. So, okay, I would like to tell one thing from this. How to get the value of I if abnormal molar mass or normal molar mass is not given in the question. So you see here, we are provided with the K2SO4 compound. So how to find out the value of I? So K2SO4 is giving 2K plus ion and 1 SO2 minus ion. Okay. 2K plus ion. Yeah, I will show the previous slide here. Let me complete this one. Okay, I will show you. 2K plus and 1 SO4 2 minus. So 2 cation and I am having 1 anion. So 2 plus 1 is 3. So that is the value of I. Okay. So you can substitute I value as 3 here in this formula. The remaining concentration, R value, T value, everything you can get from the question. Okay. So all of you know the R value, right? 0.0821. And the temperature is given as 25 degrees Celsius in the question. You can convert that to Kelvin. How will you convert 25 plus 273? So that will give you 298 Kelvin. So we have substituted that also. This is T and this is R and this is your concentration and this is the value of I. Okay. So concentration I am taking from mole by volume. That is from molarity. The molarity formula I am taking the concentration also. Clear? So let us sum. This is the previous slide. One of you have asked me the previous slide. No? Oh my God. I'm sorry. So this is the modified equation, my dear. Have you taken this down? I hope you have. Now coming to the summary of this colligative property. So colligative property depends on the number of solute and not on the nature of the solute, which is identity of the solute. And there are 4 properties. Okay. All the formulas are given here for all the properties. So please study the formulas and the definition and the concept, everything. Isotonic solution, what is osmotic pressure, what is reverse osmosis, and what is the formula to find out the value of I. Okay. So here the lesson is getting over. So I want all of you to go and revise this lesson once again and solve more number of questions from this lesson. Okay. So in the next session, we can go with a new lesson. Okay. Since we are running out of time now, I am closing the session today. In the next session, we'll start with a new lesson, which is electrochemistry. Okay. And if you're getting any doubt from the solutions lesson, you can bring those doubts in the next class. Okay. Before that, please revise all the concepts, all the formulas, solve more number of questions as much as you can. Okay. Okay, students, thank you so much. Thank you. See you all in the next class. Till then, take care.